Okay, our new topic is stress transformation. Now, until today we see how to analyze different structural problems, but at the beginning of the semester we talk about we talk about the stress, and we said that it is coordinate dependent. In fact, we choose a coordinate system to analyze a problem, to solve a problem, and we choose the most proper one among different coordinate systems. Now, therefore, if we change the coordinate system, certainly the stress values will change. And in fact, we need to know which stress values we have to use in our designs. Now let's return back to our original definition. So what we did is we just take a unit cube and in the structure, and we just choose a coordinate system. So let's choose a coordinate system. In fact, the most proper one and the simplest one is the Cartesian coordinate. In fact, so let's say that we have an orthogonal coordinate system, and so this is x, this is y, and the vertical one is the z. And then let's draw a unit cube on it. Now, on this cube, we have stress components on each face. So remember that the stress is the force divided by the unit area. And we have the stress component. So let's say that we have, this is our first stress, okay. So in fact we have the sigma in order to show the normal stress component, and we have two indices. So the first index shows the normal direction of the face, and the second index shows the direction of the stress acting on this surface. So then we have a stress component which is tangential to the surface. In fact, the normal of this surface is x, and the stress itself is in direction y. So identically we have another stress, so this is tau xz. Now on this face we have the normal stress sigma yy, okay, and we have two tangential components. So this is tau, the normal of this surface is y, and the direction of stress is x. And then we have another one, this is tau y z. So y is the normal direction of the surface, and z is the direction of the stress. And certainly on this on the top surface it is sigma zz. Now we have tau zx and tau zy. So these are the stress components that we have on a unit cube. So this is the differential or unit volume. That we have. Now, as you see, we have 9 components. So also we have 3 other. We have stresses on the other faces, but they are equivalent to these values. Let's assume that they are equivalent. So, but in fact, we have 9 stress components. Okay. Now, certainly, the tangential stress components will try to rotate this unit cube, and in fact conservation of momentum will tell us that tau xy has to be equal to tau yx. Identically, tau xz is equal to tau zx, and tau yz is equal to tau zy. As a result, we are left with, so among the 9 stress components, 6 of them are identical. So we are left with 6 stress components which acts on a volume element. A unit volume, or let's say. Therefore, we can write the stress in matrix form. Sigma xx, tau xy, and tau xz, tau xy, sigma yy, and tau yz, and the last one is tau xz, tau yz, and sigma zz. So in matrix form, these are our stress values. Okay, but the point is, calculating the 3-dimensional state of stress may not be that simple. Now we need to calculate. Let's focus on the much more simple problems, so which we call plane stress. So what's a plane stress? So in this case, we have a 2-dimensional state of stress. So the other components are 0 in fact. This is x. Let's say this is y. Then we have sigma xx. We have tau xy, sigma yy. This is tau xy. Certainly we have sigma yy and sigma xx. These are also tau xy and tau xy. Okay, now the point is, as we have said, as you rotate the this unit cube, you will see that state of stress will change. Now the point is how we can calculate the state of stress when we rotate it for different coordinate systems. Again, just take a plain stress case and let's choose this coordinate system, and in fact this is sigma y. We have sigma x here, and we have the shear stresses. Now, just say that this is angle theta, and then we have another orthogonal coordinate system, which is x prime and y prime. Now let's draw the state stresses on the surface. So we have sigma x prime, and we have tau x prime y prime on this surface. Now the point is simple. So remember that when we draw the shear force and diagram, bending moment diagrams and normal force diagrams, wherever we cut the structure has to be in static equilibrium. And therefore it is the same here. Doesn't matter how so just assume that we made a cut from a simple unit cube, okay, and therefore doesn't matter where we cut the structure, certainly it has to be in static equilibrium. Now let's say that this face has an area of delta A. Okay, so it's plane, but so it has a unit thickness. Just hypothetically, assume that it has such kind of an area. Now, in fact, then this surface will have the area delta A multiplied by sine theta, if this is theta, and this is delta A cosine theta. Now the point is simple. What we are going to do is we will write static equilibrium, so forced equilibrium in each directions. So let's first write it in x direction. So certainly sum of the forces in x prime direction has to be equal to 0, and sum of the forces in y prime has to be equal to 0. So these are the two equilibrium conditions that we have. Okay, so now let's begin by writing the sum static equilibrium in x prime direction. Certainly in that direction, first one is the sigma x prime multiplied by the area. Okay, so let's write the force. So this is equal to 0 because all other forces are in opposite direction. Now first thing is the sigma y. So the force generated by the sigma y is equal to sigma y multiplied by delta A multiplied by sine theta, and its projection onto x prime is generalized is basically multiplied by the sine theta. Okay, so this is our first force component. Now we have the shear force on that surface. Certainly the shear force generated by the shear stress is tau xy delta A multiplied by sine theta and its projection onto the x prime axis is cosine theta. Now let's pass to the other face. Now there we have the force generated by sigma x or sigma xx now the force generated by this stress is delta A multiplied by cosine theta, and its projection onto the x prime axis is multiplied by cosine theta, plus now we have the shear force. So it is delta A multiplied by cosine theta. Now its projection is sine theta. If we simplify the equation, what we are going to get for the sigma prime is sigma x prime is sigma x multiplied by cosine square theta plus sigma y sine square theta plus 2 tau xy sine theta cosine theta. Now this is our expression for sigma x prime. In fact, we can write the same equation for y prime direction. If you write the sum of the forces in and say that the system has to be in static equilibrium, you can write the forces in that direction. Now in this case, we have tau x prime y prime multiplied by delta A is 0, is in positive y prime direction. Now the situation is rather different. So first we have the tau xy component. So this is tau xy delta A multiplied by cosine theta and certainly it will make an angle of cosine theta. Let's continue below. Then on that case we have sigma x so sigma x will contribute in the direction of y prime, therefore it is negative. On the other side of the equation it is minus sigma x delta A cosine theta and it will contribute as sine theta. Now let's pass to the other surface. Plus, now again we have the shear stress. In fact, it is negative tau xy delta A multiplied by sine theta, this is the area, multiplied by cosine, sine theta, okay, and the last one is plus sigma y delta A sine theta multiplied by cosine theta. Now if you simplify this equation, what you are going to get is tau x prime y prime is equal to tau xy multiplied by cosine square minus, let's write it in a clear way on a clear page. So tau x prime y prime is equal to tau xy multiplied by cosine square theta minus sine square theta minus sigma x cosine theta sine theta plus sigma y cosine theta sine theta. Now these are the expressions. If we further simplify the trigonometric equalities, and if we rewrite the sigma x prime and tau x prime, what we are going to get is sigma x prime is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 multiplied by cosine 2 theta plus tau xy sine 2 theta. Identically, we can write the shear stress in x prime y prime coordinate system. So tau x prime y prime is equal to sigma x minus sigma y divided by 2 multiplied by sine 2 theta plus tau xy multiplied by cosine 2 theta. So this is our expression for x prime y prime coordinates. In fact, we need to calculate the sigma y prime. Now identically we can follow the same approach. Now in this case, for the sigma y prime, what we need to do is, let me draw the coordinate system once more. So this is our Cartesian coordinate system, x and y. Now we have another coordinate system, x prime y prime, and this angle is theta. So remember that this angle is theta, this is theta, if this is theta, this is also theta. Okay, now let's draw a unit, half of a unit cube here. Now we have sigma x, we have sigma y, we have tau xy, and we have tau xy. So if this, and certainly on this surface we have sigma y prime, which is normal to the surface. And tau x prime y prime is in this direction. So this area is now delta A sine theta, and this is delta A cosine theta. Now again we can write static equilibrium for this configuration. We already calculated the tau x prime y prime, so we just need to calculate the sigma y prime. So sigma y prime can be obtained from static equilibrium in y prime direction, and if you do the calculations, what you are going to get is sigma y prime is equal to, so we just write the static equilibrium in y prime direction. Sigma y prime is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 minus this is multiplied by cosine 2 theta minus tau xy sine 2 theta. So these are the equations that we have in different coordinates. Now let's look at another. So we have found that the stresses are angle dependent. So therefore this means that there exists some angles at which the stresses are minimum or maximum. And let's look at these stress values. We call these stress values principal stresses. So let's remember the sigma x prime. So sigma x prime is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 multiplied by cosine 2 theta plus tau xy sine 2 theta. Now in fact, if you want to determine the minimum and maximum normal stresses, so at which angles that we want to see, certainly this is a function of the theta at a point, because let's think that we already made the calculation and we know the normal stresses and shear stress at that point. Therefore we want to determine the maximum and minimum normal stress. What we need to do is we take the derivative of sigma stress value with respect to theta, and it has to be equal to 0. If we take the derivative of it, what we are going to get is simple. So we have minus sigma x minus sigma y divided by 2 sine 2 theta plus 2 tau xy cosine 2 theta. Now we can simplify this expression. Certainly from here what we are going to obtain is tangent to theta is equal to tau xy divided by sigma x minus sigma y let's multiply it with 2. Okay, so 2 tau xy divided by sigma x minus sigma y divided by 2. Now it's simple. In fact, this has two roots, so theta can have two values which are 180 degrees apart. In fact, both are identical, so it doesn't matter. So from here we can find the angle at which the stresses are zero. In fact, we will find two values for the theta, and if we put these values, we are going to find the two principal stresses. Sigma 1 and sigma 2 will be equal to sigma x plus sigma y divided by 2 plus and minus square root sigma x minus sigma y divided by 2 square plus tau xy square so these are the principal stresses. Sigma 1 and sigma 2 are the principal stresses. Okay, of course it has a geometric interpretation, so let's look at the problem from a different point of view. What it means. And in fact, in order to do that, let's say that 2 theta is equal to theta p, so from here we find some angle theta p1 and theta p2. Okay, now there is a tool which we call Morse circle. In fact, what we do is simple. Instead of making all these calculations, we carry the things to the space of stress. So what is a space of stress? Now, in real world, for example, for our problems, we use Cartesian coordinate system. And x, y, and z defines the location of a particle or object in this space. So what if in order to determine the state at a point by means of stress, what if I use a coordinate system which has the stress values as its coordinates. So I have on one axis I have the normal stress, and on the other axis I have the shear stress. Now at a point I have three stress values. So two normal stresses in case of a plane stress, two normal stresses, and one shear stress. So what I do is I just begin from a point and hypothetically assume that sigma x is bigger than sigma y. It can be vice versa, doesn't matter. First, I locate this stress on the axis. And then let's say that this is sigma x. So this is the magnitude of the stress, right? So this is sigma x. Then I draw a line for the shear stress. So this is tau xy. Then I do the same thing for the sigma y. But in this case, I draw the shear stress in the opposite direction. So minus tau xy. And I draw a straight line between them. Now I have the center. And I draw a circle around this line. This circle is called Mohr circle. Basically, this gives you the angle of rotation. So this angle is 2 theta 1. If you rotate at an angle of theta 1, okay, this means that so you reach to the eigenstresses or principal stresses. So principal stresses are the stress values which you have the maximum and minimum normal stresses, and in fact at this point, at these points, you don't have the shear stress. So basically you are looking for the location at which the shear stresses are 0. This is what it means. So this is, let's say, sigma 1, and this is, sigma 2. Now by using geometry, we can easily calculate the principal stresses now. It is very simple. Now this point, the coordinate of this point is sigma x plus sigma y divided by 2. And this circle has a radius. Let's say r. R is equal to now this distance is equal to sigma x minus sigma y divided by 2. Right, this distance. Therefore, r is equal to square root sigma x minus sigma y divided by 2 square plus tau xy square. This is r. This is the radius of the circle. Now, in fact, I can easily calculate the sigma 1. So sigma 1 is equal to sigma x plus sigma y divided by 2 plus r, or in other words, sigma x plus sigma y divided by 2 plus square root sigma x minus sigma y divided by 2 square plus tau xy square. In fact, identically I can write the sigma 2. Now sigma 2 is equal to sigma x plus sigma y divided by 2 minus square root sigma x sigma y divided by 2 square plus tau xy square and square root of all these expressions. So basically these are the two principal stresses that I can reach. So which means that at these points, in case of a plane stress, you reach to the maximum value of the stresses. In fact, there is a third thing. So there is a certain point at which you can reach to the maximum shear stress. Now maximum shear stress is equal to certainly to the radius So the maximum shear stress is equal to square root sigma x minus sigma y divided by 2 to the square plus tau square tau xy square. This is the maximum shear stress that you can reach in case of a plane stress. Okay. In fact, in the most general case, we can find the principal stresses directly by calculating the eigenvalues of the stress tensor or matrix. Okay, so let me remind you how to calculate so in for 3 dimensions it is tau xy, sigma x, tau xy and tau xz, and then we have the tau xy, sigma y, tau yz, and again we have tau xz, tau yz and sigma z. Now this is our stress tensor. In fact, we can calculate the eigenvalues. So eigenvalues of this matrix will give us the principal stresses or eigenstresses. So how we do it? What we do is we calculate the determinant of a matrix. Sigma x minus lambda tau xy tau xz, again tau xy, sigma y minus lambda, and this is tau yz, this is tau xz, this is tau yz, and this is sigma z minus lambda. And determinant of this matrix and saying that it's equal to 0 will give us the characteristic equation. In fact, it is straightforward for the plane stress case. So for plane stress case, you have sigma x minus lambda tau xy, tau xy, sigma y minus lambda, and determinant of this matrix has to be equal to 0, and the roots of the characteristic equation will give us the eigenstresses or principal stresses, in other words. Okay, our problem is 9.5. Determine the normal stress and shear stress acting on the inclined plane AB Solve the problem using the stress transformation equations. Show the results on the sectional element. Okay, so we have unit volume or cube. We are given the shear stress. The magnitude of the shear stress is 6 megapascals, and we have normal stress component on y-axis. We can say that the vertical axis is y-axis, so it is minus 15 megapascals, and we are asked for the normal stress on the plane, acting on the plane AB. This plane makes an angle of 60 degrees with the horizontal axis. Okay, so now let's define our coordinate system first of all. In fact, this is our coordinate system. We have x prime, and perpendicular to it we have y prime, we have theta. Theta is given to be 60 degrees, and the plane is inclined on the surface. Therefore we are asked for the normal stress sigma y prime and the shear stress tau x prime y prime. So these are our coordinate systems. Now let's write the expressions for the normal and shear stresses in y direction. So we have sigma y prime, therefore this is the normal stress. Sigma y prime is sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 multiplied by cosine 2 theta minus tau xy sine 2 theta. Let's write the shear stress now. Tau x prime y prime is equal to minus sigma x prime minus sigma x minus sigma y divided by 2 multiplied by sine 2 theta plus tau xy cosine 2 theta. Now certainly if you look at the problem, we will see that we are given some values. So sigma x is 0, sigma y is minus 15 megapascals, and tau xy is certainly minus megapascals. So let's write it here. So we have sigma x is equal to 0, sigma y is equal to minus 15, and tau xy is equal to minus 6 megapascals. In fact, theta is 60 degrees, so in radians theta is equal to P divided by 3. Now let's put the values into their places. So sigma y prime is equal to minus 15 divided by 2 minus 15 divided by 2 cosine 120 minus 6 multiplied by sine 120. In fact, this gives us the value of sigma y prime. Sigma y prime is equal to minus 17.25 megapascals. So this is the normal stress. Now let's calculate the shear stress. Tau x prime y prime is equal to, now sigma x is 0 minus sigma y. The value of sigma y is minus 15 divided by 2 sine 120 plus tau xy. The value of the tau xy is minus 6 multiplied by cosine 2 theta. Cosine 120. If you put the values into their places, what you are going to get is 101 megapascals for the shear stress. Okay, our next problem is 9.6. Determine the normal stress and shear stress acting on the inclined plane AB. Solve the problem using the method of equilibrium described in section 9.1. So I will not use the method of, I will use the general formulation anyway. So we will rotate it. In fact, we are asked for the stress acting on this plane. Now we have the shear stress. It is positive. We have sigma x. If the horizontal axis is x, so we can say that it is 80 megapascals, and so we have a shear stress also positive, which is 40 megapascals. So the vertical component of the stress is normal stress is 0. So let's write the variables again. So we have the theta is 45 degrees, sigma x is given, sigma x is 80 megapascals, sigma y is 0, tau xy is equal to 45 megapascals. Okay, so we are asked for the normal stress, in fact. So if we choose the horizontal coordinate as x, this is what it means, in fact. So we have the y here, so we have x prime, y prime, and this is our theta. Theta is equal to 45 degrees. So we are asked for the tau x prime, y prime, and normal stress sigma y prime. So let's write the equation. Sigma y prime is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 multiplied by cosine 2 theta minus tau xy sine 2 theta Now let's put the values. Sigma x is equal to 80 divided by 2, it makes 40, minus, again we have 40, we have cosine 2 theta, that is cosine 90, then minus tau xy is 45 and sine 90. So cosine 90 is 0, sine 90 is 1, and as a result this gives us sigma y prime is equal to minus 5 megapascals. Tau x prime y prime can be calculated as well. So it is minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta again. Let's put the values. So sigma y is 0, sigma x is 80 divided by 2 is 40, so this is minus 40, sine 90 degrees plus 45 cosine 90 degrees, and as a result we have minus 40 megapascals for the shear stress on the plane. Okay, our problem is 918. A point on a thin plate is subjected to the two successive states of stress shown. Determine the resultant state of stress represented on the element oriented as shown on the right. So we have two states of stresses as seen. So in the first one we have only normal component of the stress, and in the second one we have only shear stress, and we are asked for the state of stress on a coordinate system which is fixed with the horizontal and vertical axes. Okay, so first thing that we have to do is let's switch the coordinate axis and let's write the angles in fact. So certainly if we assume that this is our x-axis and this is our y-axis, which the total angle with the x-axis is 315 then. So let's write the state of stresses. So theta 1 is equal to 315 degrees. Sigma x is equal to 85 megapascals, as you see. Sigma let's say prime. Sigma y prime is equal to 85 megapascals, and tau x prime y prime is equal to 0. Now we have a second case, theta 2. In this case, the angle between the x-axis and the normal x prime is 300 degrees. We don't have any normal stress component, we only have the shear stresses. So let's write it. So theta 2 is equal to 300 degrees. Sigma x prime is equal to 0. Sigma y prime is equal to 0. And tau x prime y prime is equal to 60 megapascals. Now let's write the state of stress, the formula. I will write the whole formula. So sigma 1x is equal to sigma x prime coming from the first one plus sigma y prime divided by 2 plus sigma x prime 1 minus sigma y prime 1 divided by 2 multiplied by cosine 2 theta 1 plus tau x prime y prime 1 multiplied by sine 2 theta 1. So we don't have the shear stress component, it is 0. In fact, the normal stress components are equal, therefore the second term is automatically 0, and as a result sigma x1 is equal to 85 megapascals. Now sigma y1, identically sigma y1 is also the average of the normal stress components. So let me write the formula for it. In fact, sigma x prime 1 plus sigma y prime 1 divided by 2 minus sigma x prime 1 minus sigma y prime 1 divided by 2 multiplied by cosine 2 theta 1 minus tau x prime y prime 1 multiplied by cosine 2 theta 1. Now the shear stress is 0, this term is automatically 0, and we have again 85 megapascals. Let's write the shear stress. Tau xy1, tau xy1 is equal to minus sigma x1 minus sigma y1 divided by 2 sine 2 theta 1 plus tau x prime y prime from 1 multiplied by cosine 2 theta. So in fact the shear stress is automatically 0 because the normal stresses are 0, so this term vanishes and the shear stress is 0, and in fact we are left with 0 value for the shear stress. Now let's focus on the second case. So in the second configuration, we don't have the normal component of the shear stress, and in fact we have only shear stress. So therefore sigma x1 sigma x2 is equal to tau x prime y prime 2 multiplied by sine 2 theta 2. So the value is minus 51.961. Now sigma y2 is equal to minus for x prime y prime to sine 2 theta 2, so it is 51.961 megapascals, and the shear stress is since the normal stresses are 0, we have for x prime y prime to cosine 2 theta 2, and it gives us the value of minus 30. Now we can calculate the stress in x and y direction. So sigma x is equal to sigma x1 plus sigma x2 in fact sigma x is 85, sigma x2 is minus 51.961, so the value is 33.038 megapascals. Now sigma y is equal to sigma y1 plus sigma y2, which is 85 plus 51.961, and the result is 136.962 megapascals, and the shear stress is for xy 1 plus for xy 2, and that makes minus 30 megapascals. Now we have the problem 961. Well, the question is asking for the Mohr circles for different state of stresses, as is seen in the figure. So we have three state of stresses. In the first one we have positive normal stresses, in the second one we have positive and negative normal stresses, and in the third one we have only shear stress. So let's draw the state of stress for each, Mohr circle for it, sorry. Now what we do in the Mohr circle is we first we first draw our stress space. On one axis we have the normal stresses, and on the second axis we have the shear stresses. Now let's look at the A. So for A we have positive 5 megapascals. Let's say that this is the 5 megapascal on the state of stress, and certainly we don't have shear stress. Therefore this, in fact, for A we can say that there is no circle, it is just a point. So it is just a point for A. Now let's look at the B. For B we have two normal stresses. In one axis it is positive, and on the vertical axis, on the horizontal axis, we have negative normal stresses. So we first draw the maximum one. So let's say that this is 20 megapascals, and then we draw the negative one to the other side. So this is minus 20. In fact, there is no shear stress, therefore this is our Mohr circle for B. So we can easily see that tau max is equal to 20 megapascals. Now for the third case we have only shear stresses, so it's negative, but doesn't matter. In fact, we don't have any normal stress, so the normal stresses are zero, which means that we have one negative here, minus 18 megapascals, and the other one is positive, again 18 megapascals, because we have just the shear stresses. So this is the Mohr circle for point C, for state of stress for in C. Now 980, the question is that the stress at point is shown on the element. Determine the principal stress and the absolute maximum shear stress. So we are given a state of stress on a unit differential element. So as we see, we have only stress components in Z and Y direction. We don't have any stress component in X direction. Therefore we can easily say that this is a plane state of stress. Now first thing that we need to do is to draw the Mohr circle for this problem. In order to do that, let's draw the shear stress So this is sigma, normal stress, and this is the shear stress. So first we choose the maximum stress. Maximum stress is 120 megapascals, and then we choose the normal. So it is, we draw a line of shear stress which is 70 megapascals then, And the next thing is we draw the minimum stress. Minimum stress is 30 megapascals. And then we draw the shear stress again, so minus 70 megapascals. And in fact, next thing is we draw a line which connects these 2 points, these 2 end points. Now we are going to draw a circle which has a center of this point and passes from this point and this point. Okay, this is our circle. Now this is the first principal stress, sigma 1 or eigenstress, and this is the second principal stress, sigma 2 or eigenstress, and we have the maximum shear stress here. Now, in fact, this coordinate has the mean of this point and this point. Therefore, from geometry, I can easily calculate it as location of this point. This is 120 plus 30 divided by 2, or in other words, this is 75, this location. So this is the distance from here to here. Now let's find this distance. This will be the second objective. So certainly this distance is 120 minus 75. So this is 45 megapascals. In fact, this is, let's say, sigma y plus sigma z divided by 2, and this is sigma y minus sigma z divided by 2. And this is tau yz. Now let's calculate the r, the radius of the circle. So the radius of the circle is square root sigma y minus sigma z divided by 2 square plus tau yz square and square root of it. Therefore, we can easily calculate the radius from here. So it is square root 45 square plus 70 square root of it. So the value of the radius is 83.216 megapascals. In fact, this is equal to tau max, maximum shear stress, so sigma 1 is equal to, so first principal stress is equal to sigma y plus sigma z divided by 2 plus r so the value is 158.217 megapascals, and sigma 2 is equal to sigma y plus sigma z divided by 2 minus r, and that's equal to minus 8.216 megapascals.